Hey, differential equation students. We're going to be solving this system of differential equations where A is that matrix, and I'm going to take you through the steps. What's the first thing we need to do? We need to find eigenvectors and eigenvalues. So I'm going to define what this matrix is. I'm going to load in linear algebra, and here's the determinant that we take to find eigenvalues. I'm calling our variable here r instead of lambda. That's a little bit more consistent with this section. So I'm going to take this determinant where I've subtracted r off the main diagonal, and we're going to set it equal to 0. We have eigenvalues. Yay! Positive 4, negative 6. I'm going to work with positive 4 first to find the eigenvector. So remember, we're putting 4 up here, which is why my matrix is going to look like minus 1, minus 4, 5, 5, minus 1, minus 4. All right, what I need is some solution to this. Notice that my first coordinate minus my second coordinate should be equal to 0. So that means my first coordinate and second coordinate have to be equal. Here's a vector that satisfies that. Now, what I'm going to do is I'm going to multiply times an exponential term. That exponential term is going to be e to the 4t, and I'm choosing 4 because that's the eigenvalue I'm working with. All right, let's do that again, except now let's focus on negative 6. Down here, I've got minus 1 minus a minus 6 turns into a plus 6. So I get this matrix. All right, what does the solution look like? We'll solve 2. In this case, my first coordinate plus my second coordinate have to be equal to 0. Here's a good vector that satisfies that, 1, negative 1. And now what we want to do is we want to multiply times the exponential term, where once again, the exponent of the exponential term is our corresponding eigenvalue. All right. So this is great. Our general solution is C1 times Sol1 plus C2 times Sol2. That's what a solution looks like. Now, for this video, I'm also going to check that we have a fundamental set. So I went ahead and took these solutions and put them into a determinate. And when we simplify that, we get something non-zero. So yay, we have a fundamental set. Now what I want to do now is I want to plot some trajectories. And because I don't want us to just trust Maple, I want us to think a little bit about what this will look like. So I've moved over here, and I want to show you this image. Here's the XY plane. Here is a line in the direction 1, 1. Here's a line in the direction 1, negative 1. Because we have a 4 here, if we started on this line, we're going to see exponential growth. So we would move out this direction. Same thing, if we started off negative, that e to the 4t would push us to be even more negative. So we would head that direction. On the other hand, notice what happens if we start out in this direction. We are seeing exponential decay. So if we're in this direction, we're going to be moving towards the origin. So note what happens here. The sign of the eigenvalue determines whether we're moving towards or away from the origin. Now what if we're not on these lines? Well, if we start over here, the idea would be we would eventually move to something like this. That's what a trajectory would look like. Along this line and in, and then out. Along this line and then in, and then out. So this is what we would expect to see as solutions to our differential equation. And again, let me emphasize something here. This is where we are graphing x and y. All right, let's switch back to Maple. What I have here is the command with DE tools, and then DE plot. DE plot will do a D field plot, but it will also take these initial conditions and plot trajectories. Go Maple, go Maple. There we go. You can see we're seeing the same pattern with the arrows. What I also have are 2 sets of initial conditions, and we're following those to produce those trajectories.